Finally, we are going to talk about the transformation process between electrical energy and mechanical energy. Now, I found this YouTube clip on, and it shows you. It is a demonstration of it. Let's have a let's watch it first. Now, in this case, the long wire, we have a wire connecting to a battery and a switch. Right? The black things there are magnets. So you see the wire actually goes through the magnets. That means the wire goes through a strong magnetic field. Now, just say what's happened when the switch turned on and when the switch turned off. Okay, now let me just explain what's happening in the video. So what was happening was, say this is a top view of the magnet part. Right? I have a north on the one side, south on the other side. So between the magnet, there is a strong magnetic field. So when current goes through it, there's a force generated on the wire as shown in the video. When we turn it on, when there is a current goes through it, it either jumps up or goes down. When there's no current, nothing happens. So basically, in the last 300-400 years, we used magnet to convert electrical energy to mechanical energy. In most of, remember those toy cars when we used to play the little electric motor inside, they all have magnets inside. The magnets are used to convert electrical energy to mechanical energy. And we are going to learn more about this process. So here is the equation we use to calculate the force generated by this type of design. Okay. So let me just let's just go through the formulas. Okay. F stands for force. Okay. It's measured in newtons. I stands for current, measured in amps. And L is the length. Basically, the length of the wire in the magnetic field. Okay. Meters, and B is the magnetic field strength, okay. Measured in Tesla. So let's put it. Let's making sense of this equation. Okay. So if I have now 1 Newton, okay, is basically equals to say 1 Tesla times 1 amp times 1 meter. Okay, so what does 1 Tesla mean? If we reverse the equation, 1 Tesla is basically means 1 Newton divided by 1 amp divided by 1 meter. Okay, basically 1 Newton per amp per meter. Okay, so what does it mean? Okay, it means If the wire in the magnetic field has 1 meter of length and the current in the wire is basically 1, that's if is 1 amps. Okay, so what's happened is we're going to generate 1 Newton of force. So that's what does 1 Tesla mean. Well, of course, you don't have to remember all this, but just write down the formula. Okay, magnetic form. Well, this formula is to find the force generated by electricity go through a magnetic field. Okay, and in your book, most of cases in your book or in other notes, you'll find another equation with an n in there. F equals to n times b times I times L. And n here really stands for the number of coils. What it means is the number of wires in the magnetic field. So the idea is if I have 2 wires bonded together and the same current goes through them, the force generated will be doubled. If I have 10, it will be 10 times. Okay, so this is basically the equation we're going to use. Yep. So if I have in this diagram, if I have a wire in a magnetic field, I have a current go through it, I can easily find the force by using the equation. F equals to N B I L. In this case, N will be 1 because there's only one wire. However, if the wire, if the current is traveling in the same direction as the magnetic field, the force generated by this, say I2, by this current will be 0, because the mechanical force cannot be generated if the current and the direction of the current and the direction of magnetic field are parallel. So that's a golden rule to remember. Just remember this. So there's one more reason. So if the wire lies on an angle, if the wire lies on an angle like this, the force generated, say this is I3, the force generated will be NBIL sine theta. Because when we're using this equation, the direction of the current has to be perpendicular to the direction of magnetic field. So please always remember this. Otherwise, if it's parallel, the force generated will be 0, there will be no force generated. If it's on an angle, for I3, we're looking for, you need to use this equation, you need to put sine theta. Say sine 0 degrees will be 0, sine 90 degrees. If you do method, you may know that sine 90 degrees will be 1. So, yep, this is how everything making sense with math. So similarly, if in the magnetic field, I have maybe, well, let's use this color. Say I have a lot of electrons. Say I have a group of electrons, not one of them, just a group of them. They try to travel they try to travel through it. So during the trip of electrons, since the movement of electron produces a current, since the electron travels through it, it's the same thing. We have a current go through it. So the electrons will be pushed upwards or put upwards or downwards. There will be a force acting on the electron. So in this kind of thing, well, we can use the equation to find the actual amount of forces. But however, if we have no idea what's the current, we can't. Right? So that's why we have another equation for this type of thing. Is the force equals to the magnetic field in Tesla times the charge of the particles in coulombs times the velocity of the particles. Okay? So depending on the electron's velocity, the force varies. Okay? The force may be more or less. Okay? And also just remember it's the same story with the previous equation. Okay? So those electrons has to travel directly perpendicular to the direction of the magnetic field. Otherwise, you need to put a sine theta at the end of the equation, like the previous equations. Okay. Okay. Yeah. I'll just show you. Remember those ones. Okay. The sine theta at the end. Oh, yeah. Basically, that's it. Okay. Just remember, it has to be perpendicular.